Welcome to the Nature of Light, What is a Photon presentation by Delta Group Engineering. I'll be taking you through the presentation, which you will see, is results-centric, rather than involving lengthy mathematical derivations. Of course, for those members of the audience which may be interested, full and complete derivations can be found at our website, www.deltagroupengineering.com, in PDF format. Does a photon have mass, charge, and size? Depending upon whom one talks to, it does. The particle data group estimates its mass energy threshold to be very small, based upon solar wind observations. They also estimate its charge threshold to be very small, based upon pulsar observations. However, they do not assign, nor estimate the property of size. We calculate its mass energy and charge, to be well below the threshold particle data group values. Moreover, we calculate its diameter, to be the Planck length, to within approximately 15.3%. What is particle size? This is an open question with potentially subjective answers. However, the concept of a particle possessing point size is meaningless, that is, point size cannot be challenged, it is not forensic. We know what it can't be, that is, it can't be zero or infinity, because zero is smaller than the Planck length and infinity is larger than the visible universe. Absolute zero or infinity anything, have never and can never be experimentally measured. For instance, attainment of absolute zero temperature would require another universe to act as an energy sink for an experiment conducted in our universe. Failure of this constraint would invalidate thermodynamic principles. Considering all of this, how may we attempt to universally define particle size? We may universally define fundamental particle size, by considering all matter at rest, to exist in a state of equilibrium with the gravitational field surrounding it. Hence, for a fundamental particle represented by a point mass, at rest in its own universe, devoid of all other matter and energy, its gravitational field cannot contain more energy than the rest mass of the particle, that is, by definition, no additional energy exists. Thus, by equating the energy density of the gravitational field to the mass energy density of the particle, an equilibrium radius, that is, its size, may be computed. This definition of size has been experimentally verified to coincide with the root mean square and mean square charge radii of the proton and neutron respectively. How may we equilibrate the gravitational field? This may be achieved by letting rest mass energy per unit volume equal the spectral energy density of the zero-point field, and integrate over the frequency domain. What is gained by this approach? A solution for the cubic frequency distribution proposed by Hayes and Rueda in their quantum vacuum inertia hypothesis. B. The continuous zero-point field frequency distribution in the quantum vacuum inertia hypothesis may be substituted with a discrete and fully quantized frequency spectrum in terms of Fourier harmonics, describing the polarizable vacuum field articulated by Puthoff. C. This substitution avoids the cosmological problem of infinite energy in flat space-time because, for a solitary neutrally charged, non-rotating point mass at rest, occupying an otherwise empty and flat universe, it ensures that, 1. The gravitational acceleration field cannot contain more energy than its rest mass, and, 2. By determination of the spectral frequency limits, the energy per unit volume of the universe surrounding it is always finite. What are the spectral frequency limits? The lower spectral limit of any point in a radial gravitational acceleration field is given by omega sub PV. The corresponding upper spectral limit is described by omega sub omega. N sub omega denotes the terminating field mode obeying the integer sequence 1, 3, 5 etc. Thus, the spectral characteristics of any point in a radial gravitational acceleration field are quantized against the lower spectral limit, in accordance with the integer sequence. K sub PV represents the refractive index in the polarizable vacuum representation of general relativity, and its value is usefully approximated to unity for all fundamental particles and weak gravitational fields. How was the cosmological problem of infinite energy in flat spacetime avoided? Let's look at an example of what happens to the spectral limits of the gravitational acceleration field, in terms of quantum mechanics and zero-point field theory. In the case of a solitary neutrally charged, non-rotating point mass at rest, occupying an otherwise empty and flat universe, as the distance from the point mass increases, the value of the refractive index approaches unity. Thus, the lower spectral limit tends to zero as r tends to infinity. Consequently, as this occurs, the upper spectral limit also tends to zero. Therefore, the spectral energy density of flat spacetime, that is, when r tends to infinity, approaches zero, and the cosmological problem of infinite energy is avoided. Hence, a vanishing volume at r equals infinity contains no energy. What is the spectral limit of curved spacetime? As mass energy density increases, the terminating spectral mode at a point in the gravitational acceleration field decreases. Consequently, for a Schwarzschild black hole, the lower spectral limit of the gravitational acceleration field at the event horizon converges with the upper limit. For a Schwarzschild black hole approaching the Planck scale, the terminating spectral mode at the event horizon is unity. For this specific case, the singularity radius coincides with the event horizon, and is conjectured to be the spectral state of the universe at the instant of the Big Bang. More about this in the coming slides. Therefore, the spectral limit of curved spacetime at the event horizon of a Schwarzschild black hole may be expressed as being approximately equal to 1/4 of the Planck frequency. What does the generalized spectral equation tell us about photons? The generalized spectral equation for any point in a gravitational acceleration field is simply expressed in terms of the harmonic field mode obeying the familiar integer sequence, 1, 3, 5 etc. This equation facilitates the derivation of the upper and lower limits of the mass, charge, and size properties of the photon and graviton. What can we derive, if a photon has mass? 1. The mass and size of all existing fundamental particles and the prediction of new ones by the formulation of a single harmonic equation, that is, we may describe all fundamental particles relative to an arbitrarily selected reference particle in harmonic terms. 2. The Hubble constant and the effect of dark matter upon it. 3. The cosmic microwave background radiation temperature. 4. The zero-point field energy density threshold, that is, the cosmological influence of dark energy. 5. The cosmological evolution process. 6. The accelerated cosmological expansion phenomenon. How may we utilize the upper spectral limit to describe fundamental particles? The upper spectral limit incorporates size and mass information, representing a unique spectral signature. Thus, by applying the known masses and derived radii of the proton, neutron, and electron, their ratios may be represented in matrix form. These harmonic ratios, that is, to within 0.6% of the integer value 2, provoke the question as to how much they might change, if they were exactly equal to 2, thereby representing a precise harmonic relationship between the proton, neutron, and electron. Consequently, we have identified a harmonic hypothesis. Let's test it. Note, the derived values of the root mean square charge radius of the proton, and the mean square charge radius of the neutron have been experimentally verified. Testing the harmonic hypothesis. If we assume an exact harmonic relationship exists between the proton, neutron, and electron, how does it change the derived values of radii? The MathCAD algorithm determining the impact to the derived values is shown. R sub double pi, R sub double nu and R sub double epsilon denote the values of proton, neutron, and electron radii respectively, subject to the harmonic constraint. Notably, the deviation from initial values is less than 0.51%. Testing the harmonic hypothesis continued. How does this harmonic constraint impact experimentally measured values? Since no precise experimental measurement of electron radius presently exists, our impact analysis is limited to the proton and neutron. However, the best available estimate is less than 1 attometer, which compares favorably with our derived value of electron root mean square charge radius. The neutron radius is typically expressed as a negative femtometer squared quantity, therefore, we're required to convert our representation to a comparable form. The numerators represent the harmonically constrained derivation, whilst the denominators denote the experimentally measured values. Notably, the deviation from experimental measurement is less than 1.35%, and well within experimental tolerance. Advancing the harmonic hypothesis. From the preceding slides, the next logical step is to express a generalized ratio of terminating spectral frequencies. R1 and M1 denote the radius and mass of the subject particle. R2 and M2 denote the radius and mass of an arbitrarily selected reference particle. Therefore, utilizing this representation, it is possible to form a table of fundamental particle harmonics. What harmonic patterns form? The harmonic patterns here are very clear, no real explanation is required. One can verify the computations with a handheld calculator. The red text denotes the prediction of new particles, beyond the standard model of particle physics, based upon our harmonic interpretation. However, it must be stressed that this formulation is not unique. It is possible to deduce alternative harmonic sequences. Consequently, this approach is deemed to be a methodology, not a theory. One should note that this methodology is capable of producing masses, such as the top quark mass. The standard model of particle physics cannot. Particle mass and size summary. Electrogravimagnetics is the name we have given our photon radiation method. In this summary table, the proton, neutron, electron, photon and graviton radii were not derived utilizing our harmonic interpretation. All other particle radii were. The black text denotes particle data group data and EGM predictions prior to 2008. The red text denotes 2008 particle data group data. The blue text denotes 2008 EGM radii predictions of existing particles. The green text denotes 2008 EGM radii and mass energy predictions of new particles. The magnitude of average change in EGM radii from previous values due to 2008 particle data group revision is 3.5%. The EGM radii and mass energy of the gluon is set to not applicable, due to its mass energy being subject to conjecture. However, it is possible to express the radii and mass energy of the gluon in a manner consistent with EGM methodology, if assumptions are articulated. What errors are associated with our photon radiation method with respect to particle physics? The only prediction displayed in this table, formulated utilizing our harmonic interpretation, is shown in red text, that is, the top quark. All other predictions were derived utilizing our terminating spectral frequency relationship. This table compares our EGM prediction to expert opinion or experimental measurement. As can be clearly seen, the correlation is quite remarkable. I would like to draw your attention to the classical proton and Bohr radii, which are not experimental determinations, but the official values listed by the National Institute of Standards and Technology. Please also note that the error associated with the mass of the top quark is the largest. This is due to the fact that, to calculate its mass, an estimate of the root mean square charge radius is required. A minor correction of the root mean square charge radius of less than 1.671% produces the experimentally determined 2008 mass energy value precisely. The highlighted 2008 Hammer and Meissner results denote the average values of two unique approaches, that is, superconvergence and the explicit PQCD continuum. Importantly, the magnitude of the average error associated with the whole table of predicted values against expert opinion or experimental measurement is less than 1.12%. What is R sub nu physically? It was mentioned on a previous slide that the neutron radius is typically expressed as a negative femtometer squared quantity, therefore, we were required to convert our representation to a comparable form. We have developed a technique for readily converting between forms. To invoke this technique, one must appreciate the physical meaning of R sub nu. 1. It denotes the zero-point field equilibrium radius. 2. It coincides with the neutron mean square charge radius, conventionally represented as a negative femtometer squared quantity. 3. It marks the transition of the positive core to the negative shell, that is, when the charge density is 0. And 4. R sub dr marks the minimum charge density. Testing the harmonic hypothesis. Again, arguably, the greatest test of any methodology, theory or physical concept, is whether or not it may be applied, and experimentally verified on a cosmological scale. The harmonic hypothesis may be tested on the cosmological scale by assuming that a. m1 equals the initial total mass of the universe, m sub I. b. m2 equals the present total mass of the universe, m sub f, which is equal to m sub I. c. R1 equals the initial size of the universe, r sub I, that is, at the instant of the Big Bang. d. R2 equals the present Hubble size of the observable universe, r sub f. Next, let St sub omega, to the 9th power, equal the ratio of the minimum gravitational lifetime of starving matter to the present Hubble age of the observable universe. Notably, electric charge and spin angular momentum are not represented in the harmonic hypothesis, because the universe does not possess a net charge or spin. Thus, if we wish to develop a scaling methodology applicable to all scales of reality, charge and spin cannot be included, that is, the present cosmological values of zero net charge and spin cannot be reverse engineered to non-zero initial values. How can one scale a zero quantity? Testing the harmonic hypothesis continued. Respecting conservation of mass energy, we immediately recognize that the initial and present total mass values of the universe are equal, that is, m sub I equals m sub f. Hence, the harmonic hypothesis applied to cosmology takes the form shown, where the minimum gravitational lifetime of starving matter is given by Planck's constant divided by the mass energy of a photon. By inspection, this equation appears plausible, because it is a simple scaling relationship, that is, the ratio of the present Hubble size of the universe, to its size at the instant of the Big Bang, is proportional to the ratio of the minimum gravitational lifetime of starving matter, assuming infinite time as a non-physical parameter, to the present Hubble age of the universe. Note, the above assumes that the universe is flat, as experimentally confirmed by the Wilkinson microwave anisotropy probe. Harmonic hypothesis continued. Utilizing the harmonic hypothesis, expressions for the Hubble constant and the cosmic microwave background radiation temperature may be formulated. The harmonic hypothesis may be transformed according to the relationship shown, where K sub W equals Wien's constant. Note, St sub T, H sub alpha, lambda sub x, which appeared in an earlier slide, and mu, are forwardly derived constants. Importantly, H sub alpha denotes the Hubble constant at the instant of the Big Bang. What cosmological results did we achieve? 1. A Hubble age of 14.6 billion years. 2. A Hubble constant of 67.1 km per second per megaparsec, that is, to within approximately 4.7% of particle data group estimates an experimental measurement by the Wilkinson microwave anisotropy probe. 3. A cosmic microwave background radiation temperature of 2.7248 Kelvin, that is, to within 0.01% of the physical measurement by the Wilkinson microwave anisotropy probe as reported by the particle data group. 4. A galactic radius of 8.1 kiloparsecs and total mass of 6.314 by 10 to the 11 solar masses, that is, to within approximately 1.34% of the particle data group value, and 6% of the average of two community estimates of total galactic mass. This graph demonstrates the derived relationship between the Hubble constant and the cosmic microwave background radiation temperature. The equation shown is expressed in a slightly different form in relation to the preceding slide, but it's the same equation. Please just ignore any notational differences, it's purely cosmetic. Of particular and obvious importance is the shape of the curve. Although the curve has the classic blackbody radiative shape, the blackbody law was not utilized in the formulation of the curve. Another important feature of the curve is that it illustrates a cosmological temperature at an instant prior to the Big Bang of 0 Kelvin, and rose to its maximum value very rapidly. This graph demonstrates the rate of change of the cosmic microwave background radiation temperature in the time domain with key physical features represented, that is, local minima etc. This graph demonstrates the second derivative of the cosmic microwave background radiation temperature in the time domain with key physical features represented, that is, local maxima etc. This is an important graph demonstrating the rate of change of the Hubble constant in the time domain with key physical features represented, that is, local maxima etc. Next, we shall overlay some cosmological information to help us interpret this curve. With the graphical information overlaid, the distinction between cosmological inflation and expansion is very clear. One sees that the cosmological expansion period commences at the instant of maximum positive Hubble derivative. Hence, any cosmological periods prior to this specific event must be inflationary. Of particular importance, one should note that the rate of change of the Hubble constant in the time domain is presently positive, which explains the experimentally observed accelerated cosmological expansion phenomenon. The standard model of cosmology cannot explain this, but our photon method does. This graph demonstrates the second derivative of the Hubble constant in the time domain with key physical features represented, that is, local minima etc. If we graphically represent the magnitude of the first derivative of the Hubble constant in the time domain, we may dissect the cosmological inflation period as follows. In terms of the cosmological evolution process, this is the most important curve we have shown so far. In this form, it is quite apparent that the cosmological evolutionary process may be dissected into four distinct intervals termed primordial inflation, thermal inflation, Hubble inflation and Hubble expansion. Primordial inflation refers to the pre-Big Bang period when, according to the EGM method, the universe was literally an inside-out sphere. As strange as it may seem, a complete mathematical description of turning a sphere inside out without sharp creases or tearing, termed sphere eversion, is well described and understood. So, the EGM-derived characteristic of sphere eversion has solid mathematical grounding. Another way to visualize the universe prior to the Big Bang is by considering it to be analogous to a Schwarzschild black hole, but with the radius of the singularity being the outer radius of a sphere and the inner radius being the event horizon. At time t equals 0 the Hubble constant and cosmic microwave background radiation temperature have values of positive and negative infinity respectively. At the moment, when the inner and outer radii were equal, that is, the singularity radius coincided with the event horizon, the Big Bang occurred, and all physical laws became real. The temperature was 0 Kelvin and the magnitude of the Hubble constant decreased from positive infinity to h sub alpha. From the instant of the Big Bang to the instant of maximum cosmological temperature, the magnitude of the rate of change of the Hubble constant decreased to 0, as shown by the graph. After this, the rate of change of the Hubble constant in the time domain became positive, explaining the experimentally observed accelerated expansion phenomenon. All of the graphs shown were generated utilizing a deceleration parameter of 0 for two reasons. 1. Because the Wilkinson microwave anisotropy map satellite shows that the universe is almost perfectly flat, and 2. In order to calculate the Hubble age and size of the universe. However, if we reapply the EGM method based upon the derived deceleration parameter specified in the quinta-Essentia series, we obtain precise non-Hubble values in favorable agreement with the standard model of cosmology. In fact, we calculate a present deceleration parameter of -3.314 by 10 to the -4. It is important to emphasize that the standard model of cosmology has not produced the accelerated expansion phenomenon or negative deceleration parameter determination. What do the results demonstrate? 1. The magnitude of acceleration in a constant gravitational field may be decomposed into a spectrum of frequencies obeying a Fourier distribution. This methodology unifies all matter, on all scales. 2. All matter may be treated as graviton radiators, hence, all starving matter, including black holes, will eventually evaporate as ejected gravitons. 3. A graviton may be described as a conjugate photon pair, hence, evaporation as ejected gravitons is actually evaporation as ejected photons. 4. The Hubble constant and cosmic microwave background radiation temperature are related. 5. The influence of dark matter/energy upon the Hubble constant and cosmic microwave background radiation temperature is less than 1%. 6. The constitution of the universe is greater than 94.4% gravitons, less than 1% inexplicable dark matter/energy, and 4.6% atoms. 7. The average cosmological value of zero-point field energy density makes commercial energy extraction from the zero-point field unlikely, because the available zero-point field energy is very small. Notably, the volume of the Sun only contains the equivalent zero-point field energy of approximately 4 grams of matter. Moreover, the Sun has approximately 1.3 million times the volume of the Earth. The standard model of cosmology maps the cosmic microwave background radiation temperature over time in accordance with this diagrammatic representation. It is important to appreciate that the EGM method also produces these results, to a degree of precision substantially beyond the standard model of cosmology, simultaneously with the determination of the Hubble constant. Conclusions. Experimental evidence questioning the existence of dark matter has been published in Nature. Thus, we propose that 1. All matter radiates gravitons. These gravitons may be modeled as conjugate photon pairs. This radiation is the energy source for the energy sink conventionally termed the space-time manifold, resulting in the curvature described within the framework of general relativity. 2. All starving matter will eventually evaporate, returning the energy borrowed soon after the Big Bang, back to the zero-point field. The evaporation period is greater than 4 by 10 to the 22 years, that is, approximately 3 trillion times the present Hubble age of the universe. 3. Dark matter may be explained in terms of gravitons, and dark energy is simply the Casimir force acting on a cosmological scale. 4. Most importantly, matter is just a condensed form of photons. Hence, a photon is a propagating piece of matter. Well, I hope you've enjoyed the show. Please feel free to contact me by email or phone. The details are on the screen.